Hello, welcome. We're going to talk about the mapping revolution. My name is Tal Babaioff. I'm leading the mapping and localization in Mobileye, and we're doing it inside an establishment called RAM, Road Experience Management. And the big question is, why are we talking about mapping? We're a company doing smart vision for safety, for autonomous driving. Why do we need mapping? And you can think about this situation and consider why an autonomous vehicle needs a map. What's going on beyond the end of this road? You don't see anything because it's over the hill. And this is one of the occasions in which both a car and a human driver have a limit, but you don't have to stick with this limitation forever. We can actually overcome it and embed a map. It gives us the information below the horizon, what's beyond the sensing of the sensors. It gives us information about traffic light, to know which traffic light belongs to which lane and where is the stop line relative to that traffic light, which is a really hard problem to do while you're doing driving and sensing. And it allows you to solve problems like understanding if this pedestrian is on our road or on the sidewalk, or if this vehicle is inside our lane, by having a map which helps taking this hard problem and making them simpler problems. So here we see it from an autonomous driving point of view, just like the experience that you drove today. And what we have here is the car and the map projected on the images in 3 different views from each of those cameras, and also a top view which aggregate all the information together. And you can see how much the map enriches the environment, makes the situation easier to understand this pedestrian crossing on the road, giving you an understanding of who needs to give priority to others, and so on and so on. Now, mapping is not something that just Mobileye is doing. Others have been claiming that they have been doing mapping for hundreds of years, and even HD mapping is talked about. And the common approach is creating a vehicle with a LiDAR sensor, and then driving something like 100 cars of fleet for creating a 3D model, and do that to create a map. And the real problem with this is it's very, very expensive. You do it only where you select to drive. You actually have to pay for the drivers. The data flow is amazing. It's terabytes of data. And this is something you cannot really do at large scale. It has coverage and so on. And because of all 10% of the road changes yearly, and the problem is that you have really millions of kilometers of road. This does not scale up to something that you can build an autonomous vehicle around it. And we said that we need to address it differently, and we would create our own map which would give you the environment to drive on. But we have maps today. You've been driving with your Google Maps or Waze, and you're driving and you're happy with it. It has great details. Why do we need something else? Now, think about the last situation where you were supposed to take the right turn and you continued straight. How long did it take for Google Maps to understand that you missed the turn? The real problem is localization. The localization in normal GPS and normal maps is within 10 meters, 5 meters more. You would be in the oncoming lane if you count on that information. And we give a centimeter accuracy within your lane to give you the right information based on localization. On top of that, the other alternative would be to go to a precise GPS. If the GPS would have been better, we would have gone to cheaper maps with precise GPS, but this is something which does not work everywhere. You have tunnels, you have urban canyons, you have jammers. You cannot rely on that. We want to have something which is independent, and precise GPS by itself does not solve the map creation problem. So you've been here at Mobileye, and we've been doing computer vision for 20 years, and we've been running this in every road on the planet, and we've been detecting all the objects that the driver is looking for while he's driving. So we are looking for lane marks, and traffic signs, and road edges, and reflectors. And all of this object is something which we can actually harvest and embed into our map and build our map upon this information. So this is where we're coming from. We are taking the ADAS fleet. We have around 45 million cars driving today with our data, and have them being our large crowd of vehicles to give us great coverage, and have low time to reflect reality. So if the road changed today, we want to be able today to create a new map in this area that your vehicle would drive in. We're building our sensing based on the camera. The camera is already in the vehicle. Each vehicle has a GPS and a cellular modem from 2018 because of eCall in Europe. So we don't add any hardware. You can actually have real big, large-scale crowdsourcing. We moved from very human-intense map creation approach to a fully automatic map creation, which means you can do it fast and you can do it cheap. And because of that, you can do it in large scale and with small refresh rate. We are not uploading any images or video from the car. So the packages coming out of the car is very, very tiny. We can do it based on 3G modems. We don't have to wait for 5G. We don't jeopardize privacy because of that. And this is done by doing a lot of computation on the client, on Mobileye chip. We are really, really doing things on the edge. When we send data out, we send 10 kilobytes per kilometer. It means that your vehicle driving 20,000 kilometers a year or 15,000 miles would send 200 megabytes of data. This is roughly 60 songs. My daughter does it in an hour. We have clients for our maps. Because Mobileye has a great penetration to the ADAS and AV, each of those customers is a potential customers for us. So we're not creating these maps for fun. We have actual real customers for that. And we're supporting it not only for the autonomous driving, but also for the vehicles which would be selling from today. L2 plus application, giving the driver the ability to drive without hands on the wheel, or giving him better safety based on integration of map into the environment. And last but not least, because we have a smart agent in the vehicle which is always connected, we can start asking questions about dynamic events. Where do we have traffic jam? Where do we have hazard on the road which we need to react to? And each of our smart agents can report back to us, and we can integrate that data, and we will talk about that deeply. So we are here today, and we have been talking for years about RAM, but we are today in the step which we are ready to map the world today. We have vehicles from BMW and Nissan driving today, sending us data. We have Ford, VW, and NIO planning to send us data from their vehicles starting from next month with VW. And we would create maps of the world from today onwards. And the goal is to have a fresh map of all of Europe by the end of Q1 2020. Our biggest value is by our automatic process, our ability to work with small data sizes, both in harvesting and in localization, so we can work on 3G today. We're testing our maps today daily on our autonomous driving. You just drove one of those. So we have feedback from the end users, and we know if we're good enough or not. We are well accepted by most OEMs for harvesting an L2 plus application. And we don't really have to wait for the autonomous revolution to start using our maps. We have real value of our maps with customers from today. And we're aiming on 10 centimeter accuracy. When looking on RAM, we have three main stages in our mapping. First is harvesting. Each vehicle drives on the road because he's driving, and he tells us where he drove and what he saw while driving. This data is encrypted and anonymized, so we can send it in a way that does not jeopardize the person's privacy. For example, we are cutting off the start and the end, and we are adding random gaps inside the drives. And all of the data is sent to the cloud for an aggregation. We have been working on AWS Cloud. In the aggregation step, we're both creating a high-definition crowdsourced roadbook, and we're preparing that for distribution. The next step would be to distribute tiles to the cars. These tiles are actually very, very small, around 100 kilobytes per tile, so tiny. And the last step would be localization, the actual use of map. As we said, you can have great maps, but without good localization, nothing worth it. And this is what we've been doing. We've been collecting data worldwide by BMW and Nissan since the start of this year, and you can see how well we are represented. Each of those yellow lines represent a vehicle which drove somewhere. And this actually resembles where you have population over the world. Okay, you have all Japan covered, entire Europe, US. You can see in Europe that this is covered well. And today we're still in small numbers. We expect 10 times more vehicles by the end of next year, almost 20, which means that we would not only be able to map the entire world, but we would be able to map most of the roads within a day or less from fresh data. You can see in US nice coverage from BMW cars in the East Coast and West Coast, and we would have a US-based OEM selling US vehicles with much higher penetration next year, which would allow us to have great coverage of the entire US. If you think about numbers, we are collecting roughly 2 million kilometers daily. We have been collecting over 300 million kilometers of roads coverage until now. And you can see that this is increasing nicely. And this, as I said, is with tiny numbers. Today, the 2 million kilometers, we look at it as if 100,000 vehicles. We expect to have over 1 million vehicles in EU by the end of next year, and over 1 million of vehicles in US by the end of 2021, which means that you would have maps with high refresh rate for each of them. I talked a lot about harvesting. This is how harvesting looks like. This is what actually sent from the vehicle. A 3D representation of the road position, of the lane marks, of the traffic signs, of the traffic, of the poles. And all you sending is very compact representation. No video is sent from this data. The hardest point is actually doing the aggregation. We have multiple drives, and we want to say that this drive and this drive drove on the same point, and that they are seeing the same object. And it's actually trying to match them so that we would see that they are driving together in the same point. Now, this could be considered a small and very easy problem. You have two vehicles, they drove in the same environment. You know that this is the same traffic light, this is the same stop sign, this is the same dinosaur sign, and then the matching is very, very easy, and the alignment is easy. But the real situation is actually much more complex. The sensing is not perfect. What you see in the world reflects the fact that you have occlusion by other vehicles. So one vehicle might not see the second traffic light, and the first vehicle would see two traffic lights. And in some cases, we may have even a misclassification of the sign by looking at it as another sign. And then the problem becoming much, much harder because you have errors everywhere. And this is how it looks like when we take many, many vehicles. Each of them gave us a single point, every point. We are trying to aggregate and align each of them one on top of each other. And you can see how well the alignment well here, because we are representing the lane marks and the road edge and the poles in a very high accuracy just by looking on this image. And this is done on a small patch, but this is actually done globally whenever we create maps. So where are we today? We started this year by creating the entire map of Japan. We've done that in a single press of a button, less than 24 hours. This was done since 5 more times. And we've done that in a way to create maps for Nissan. And Nissan have been selling vehicles using this map since last September. And the entire map of Japan is only 400 megabytes. It's tiny. We have separated this map into tiles of 1 kilometer square. Each of them on average weighs 30 kilobytes. We're talking now on more interesting map tiles with urban scenarios, which is 100 kilobytes with them. That map has over 1.1 million features, 320 signs, 300,000 poles, 2,500,000 lane marks, and it represents well the highways in Japan. Now, this was done based on preceding. We had some car fleet driving there and collecting data for us because we didn't have harvesting back then in a large scale. And this already reached production. Nissan is selling the ProPilot 2 today. They are giving you the ability to drive hands-free by using our map. They are giving you the ability to do overtake, which is also looking on our map to see that there are empty lanes or there are enough lanes to make this overtake in. And they recognize the HD map localization and utilizing in the brochure to the driver. The next step is creating maps from production RSDs. I show you the harvesting that we've done, and we have harvesting worldwide. This is how it looks like. We took map, created it from BMW data, and we overlaid it on a video which we had prior to that from our normal testing. And what you can see here is that on the map, we project, on the image, we project the map. You can see how well the signs sit, how well the traffic, the lanes sit. The blue lines is what we call drivable paths. It's the position in which most vehicles drove. And you can see that we have perfect roadbook created from these production RSDs. We can take this same concept to a roadbook created here in Jerusalem and looking on the extreme situation of rain at night. At rain at night, we actually have very, very bad reflective surface. You can hardly see the lane marks. And still, we can provide perfect localization. We can give the vehicle information where the lanes are even without sensing the lanes. And we can allow the vehicle to drive autonomously on this environment in a conditions which would normally you wouldn't think that you would put an autonomous vehicle driving, because the sensing of the lane marks is almost impossible in this harsh rain situation. On top of that, we have been taking our map creation scenario into different cities in the world just to showing that we can do what others consider as impossible, doing very high deep urban mapping. We have concentrated on Europe because Europe was easy because the BMW is selling more cars there. So that's an example of Berlin and the center circle in Berlin. Another example is Paris, Arc de Triomphe, and the areas around it. What we see here is the red points is poles, the blue points are traffic signs, and the green lines are lane marking. We created a huge map above 5,000 kilometers of road around Volkswagen factory in northern Germany. We created a similar map in Hanover, which is also driving distance from there. We created another map in Düsseldorf. And we said, well, US should be also represented, so we did Beverly Hills and London. This is a Heathrow Airport, and what you see here is this junction. You can see how well this junction was mapped and modeled by our mapping environment. And we took the entire drives around San Francisco, creating map in San Francisco as well. And each of you, if you want to look, we can go and deep dive into the map in the areas that you live in. In parallel to that, we took another project and we said we want to have Israel as a sandbox. We have Mobileye headquarters here. Here we need to show that autonomous vehicle is driving. So we started creating a roadbook in Israel showing that you can drive all roads above 70 kph by the end of this year. Each of those roads has a map which is equivalent to the map which you drove in our AV demo, and you can drive it with our AV hands-free on each of those roads. So this is something which is done on a weekly basis. We enrich, we add more drives and create the map again. We've done here above 2,000 kilometers of map length, and it's built from 10,000 random drives. This is, from our point of view, a sandbox because we collect here also video, so we have much better validation and verification from this fleet. So here we are, and we are able to map the world. We're planning to run and create the entire world automatically and have fresh maps. But there is a little more above that. So we started by taking our smart agent and doing maps for ADAS and AV application. We map the road and the objects around it so that we support validation, localization, and give the autonomous vehicle all the information that he wants. But the next step would be to take our smart agent and do asset mapping. We have utility companies which ask where is our Manholes or drainage, are they clogged or not? We want to know where telco cabinets and is lamps operational or not in the street, and every other smart city survey and asset management. Understand if there is surface water because of a leak, and so on. So we can do all of that. We've been working on it, and we can do that. And the next step is to move from asset management and doing this asset analysis to a next step of intelligent agent, being able to give whatever a human driver would be able to tell you. We would do it from our camera. Not only all relevant road elements, but also every event. And on top of that, we are moving towards the next generation of collecting non-semantic information, which would give us another layer and another information for map creation and map validation. So here's an example of asset mapping here in London or Japan? In Japan. You can see poles detection, arrows detection, traffic sign, zebra crossing analysis, manholes, and so on. Same in our backyard, the same route that you drove today. Sensing of bumps, zebra crosses, manholes, poles, bumps again, and so on, created live by our sensing. Think about if we collect this from many, many cars, we can create a map, we can create a consensus between all those vehicles, and for each point here, we know where we are, we can put it in a precise position inside a map. When we think about our data value proposition, what we can do, we have different pillars which we can address. The asset mapping, as we said before, being able to give city operations, gives them understanding of road conditions and changes over time, potholes, construction tracking, streetlight status, and real-time hazards. If you think about city planners, we can give them a survey about where pedestrians and vulnerable road users are, where do you have parking issues and where do these people park. Understanding of road safety from vehicle driving and accidents and semi-accidents, so that you can know where you need to improve your infrastructure and actual traffic flow. We can support public transportation by pedestrian survey, traffic flow, and real-time analysis. And of course, we can do fleet management for every driver, give him a driver score, do a better routing based on a road safety score, and also do or understand the real-time alerts coming from these drives. The real benefit is everything is with high refresh. Data is never out of date. Great coverage because you have vehicles whenever you want them. No human in the loop. It's relatively reasonable pricing, high accuracy, and some things which are unique. I said about potholes and electric boxes and pull some visuals to give an understanding what this looks like. We have great demand for each of those applications. Some of it is represented in the ordinance survey activities, which was public a few months ago. To give you a feel, we asked from our vehicles to tell us where they saw a stop sign. And you can see how well we cover this thing, which happens on every corner of every small street in the US. And you can see that the fleet of 150 vehicles gives us this coverage in no time. This tells us that whatever feature a driver can see, we can do for you in relative timing. And the real game changer here is the ability to do it with a unit which is always connected, and we can support over-the-air update changes. So we can update the software. Whatever you are sensing today, you want to detect now blue phone booths, we can implement that, add it to the software, and a month later you would have a full understanding of a new feature which was never harvested until now. As part of our survey, we understand that the customers are normally cities which are using the ESRI application, and we integrated our sensing into ESRI. So think about this traffic light in Manhattan, which was detected by a camera. We are able to integrate that information into a map and understand where this traffic light is and output the information to an ESRI layer. And you can see the Manhattan traffic lights represented in the ESRI layer by the aggregation of many, many drives. And you can go back from this specific traffic sign back to the image where it was detected if you want. The image is not sent. If we want, we can consider that as well. We have today a nice fleet in New York City, and we've been spending some time analyzing the data coming from it to show you some of the features which we can actually give you. So we can think about vehicle overspeeding, speeding violation, construction area behavior, public transportation, pedestrian on highway, jaywalking, and does cyclists use their lane. So this is an example of speeding violation. We take this road between Gotthard Bridge and Korean War veteran parking, and it normally has a 45 miles per hour speed limit. But when looking on the fleet of cars driving there, you can see that many of them driving around 60 miles per hour. So giving this an information allows you to understand where does people speed, and if they speed in area which is segregated and closed, and this is okay, the speed limit is wrong, or are they speeding where you have a lot of pedestrians? And this is actually bad, because you don't want them to speed where there are a lot of pedestrians. There is a good reason why there is a speed limit in these roads which have pedestrians on them. This is another great example. What we see here, the heat map, is where bicyclists are actually driving. And the pink lines is what the grid of bicycle lanes which was created in New York City. And it really shows that this should have been a bicycle lane. And this bicycle lane is never used because people which are driving here want to continue like this. And they are not willing to take a left turn and a right turn, they want to drive straight. So from this map you can see that some bike lanes are actually well represented and used, but when you make something which is really does not make sense, people select not to use it. And they would drive on a road without a bicycle lane even if they can. We can detect construction area from our cameras. We can look on the speed of the vehicle, which decreases as a function of this construction area. We can notify the cities that the construction which was supposed to end last Thursday is continuing, and understand much better what's the situation in the city. We may look on pedestrians and see if they are crossing on zebra crosses or just jaywalking around the street, and understand what's the impact and do you need to add why is this happening. Give information for city planners. This is an example of pedestrian count near bus stops. We can give information based on hours, based on time, so that they can understand if you need to send more Ubers to this area. And on top of everything, because our cameras detect pedestrians, we can look not only on the speed of the vehicles, but if you see pedestrian crossing on the highway. Another coverage image shows the speed of the lanes. Whenever it's more blue, the faster the lane of Los Angeles in a day. We can have this information on every city in the world, and you can utilize it to understand the impact or the traffic flow of the city and plan accordingly and use it for many routes. So this has been REM in a nutshell. We believe that HD map will continue to penetrate the ADAS market. We have Nissan already driving it, Volkswagen would use it soon, and we see other OEMs in the negotiations towards embedding the maps for future projects. For any application which is aiming on full autonomy or high autonomy, we trust that they would use HD maps because HD maps are actually a critical sensor for them, and we believe that our maps is the right thing for them because they are updated very fast and they are at scale, meaning that you are not limited and you can actually have this application in every position. We're moving from geometrical analysis to semantic layers to give priorities and insight on top of that, priors and insights, to real-time event. All of those would serve the autonomous driving. Roads were built for humans which see. We added traffic signs for humans to read. We added lane marks for humans to sense. The camera is the right sensor to leverage the crowdsourcing mapping because it's affordable, it's eyes on the ground, it's in every vehicle anyhow, and the data is very, very rich and relevant for map creation, and it's much more detailed over LiDAR or radars. For our mapping, we see growing demand for the high accuracy survey information and the real-time updates of the map, both for cities which needs to move to the digital area in their planning and day-to-day management, and also being able to utilize our technology solution on larger scale. We are in a very unique position for this situation. We moved from presentation saying this is what we want to do 5 and 4 years ago to actually being able to produce maps at large scale. And we have great opportunities ahead based on the fact that we have here today something which nobody else has. Thank you very much.